Hi everyone, I'm going to talk today about chapter 1, which is our first introduction to motion, first introduction to anything actually. So we'll go through some motion diagrams, talk about the different quantities we use to describe motion, including position and time, and then velocity and acceleration. And then we're actually going to start with unit conversions and significant figures. Okay, just to start with a kind of big picture of where we'll be going in for a lot of the semester, we're just covering the motion and how to describe motion. So the first couple of units called kinematics is really just a description of motion. So that's kind of chapters 1 to 4. We'll start with just, chapter 1 gives an overview and then restrict our analysis to motion along a straight line, so one-dimensional motion, and then look at two-dimensional motion. And then once we finish that, we'll move on to more forces, where we can start thinking about what is causing the motion, right? So not just describing it, but how do we explain it? And so that the general area is called dynamics. And so that's chapters 5 through 8, and then 12 and 13 for more extended objects and gravity. And then in between that, we'll take a different approach, which is not a force-based approach, which has to do with conservation laws, so conservation of energy and momentum, or ones you may have heard of before. So if we think of the big picture of physics here on the right, let's see, sorry. So we can divide physics into a number of different topics. The focus of this semester is mechanics, which is the study of motion. And again, like we said, kinematics and describes motion, and dynamics talks about the causes of it. Next semester, we would hit electricity and magnetism and some of the optics. And then heat is actually, for our physics majors, is done in a separate course of thermal physics. Okay, so 4 types of motion. I kind of talked about this a little bit, but so the first part that we'll just do is linear motion, looking at motion along a straight line. We can learn a lot about the basics of motion just from that, and then we'll analyze motion in 2 dimensions, which would be projectile motion. Circular motion is another example of 2D motion. And then finally, we'll look at rotational motion, which is when an object is spinning, in addition to maybe translating. Okay, so just to start off with units, we will be using the SI units, the System International. The length unit is a meter. Mass is in kilograms, and time is in seconds. So those are probably units that you are familiar with. Okay, and then, so let's start with a unit conversion. So we're going to do 2 examples here. One is going from miles per hour into meters per second. So I'm going to turn on my camera here in a second, but we want to do 60 miles per hour, and we want to convert that into meters per second. And we're given that 1 mile is 1609 meters. So let's switch to the camera. Okay. So we want to do our conversion, right? 60 miles an hour into meters per second. So we're often going to be working in meters per second in this class, and it's nice to know when we do this problem, we'll have just kind of a rule of thumb for converting between the 2 of those. Let's go down a little more so it's a little bit bigger. Okay, so when we do unit conversions, we want to set up basically fractions that will take our initial number and multiply it by a series of fractions. And focus there. Make sure we're in our best focus. Okay. And so each fraction is going to have a value of 1. So we're not actually changing the number, right, or the quantity that we're talking about, but we are going to change the units. So the numerator and denominator are going to have different units, but they'll be equivalent, right? They'll just be they'll be measuring the same thing, but in different units. So let's first convert miles, right? So if we want to get rid of miles on the top and we want to end up with meters on the top, we're going to put our mile unit on the bottom and our meters on the top. And we were told over here, right, that 1 mile is 1609 meters. So those are equal to each other, right? So that fraction is 1, even though the units are different. Okay, now we want to convert our time. So we need to go from hours on the bottom to seconds on the bottom. So we could do this in one conversion if you know that 1 hour is 3,600 seconds. That's kind of a useful conversion to keep in mind when we do our time conversions. That's just 60 seconds times 60 minutes, right? Gives us 3,600 seconds. But we can do it in 2 steps for the first time too, just so we see how that works. So we have 1 hour up on the top, and then we can first go to minutes. So we'll say 60 minutes. And then we're still not quite there, right? Because we want to end up in seconds. So we have 1 minute on the top and 60 seconds on the bottom. And so let's just check our units, right? So we have a mile on the top, cancels out with a mile on the bottom. So that leaves us meters for our distance. That's good. And then for our time, we have an hour on the bottom, an hour on the top, a minute on the bottom, a minute on the top. So they cancel out. And so our ending up units are meters per second. So if we pull out what survives here, we have 60 times 1609. And then on the bottom, we have 60 times 60. And then the units that are left are meters per second. So let's use Python to do our calculation here. Okay, and 60 on the top and the bottom actually cancels out, right? So we could get rid of one of those. So we want to do 1609 divided by 60. And that gives us 26.8 meters per second. So this is a good example. In this class, we are going to always just keep 3 significant figures. So 1, 2, 3. If you have a 0 in the beginning, like let's say it was 0.0 whatever, 268, these leading zeros don't count. Okay, so but in general, we're just going to stick with 3 significant figures. We're not going to belabor the significant figures in this class. Okay, and so we should box our answer here as well. All right, so then the second problem on the slides, if I could get this out of the way. Oh, I need to hide that. Okay, so now it's saying the second one is the density of the sun and converting that. So the density of the sun is, I'm just going to write down on my sheet what we're doing, 1,400 kilograms per cubic meter. And we want to convert that to grams per cubic centimeter. Okay, so go back to our camera. Okay, so here's number 2. We want density, which is often, this is the symbol rho, R-H-O, it's the Greek letter, and that's often used to represent density. Okay, so we'll start density here, right? And we have 1,400 kilograms per cubic meter. So again, we'll multiply our fractions here, and let's do the mass first, right? So we have the kilograms on the top, we want to get rid of it. We put kilograms on the bottom, so those will cancel out, and we put grams on the top. And we know from our units that a kilo is 1,000, right? So a kilogram is 1,000 grams. Okay, and now let's do our distances. So we have a meter on the bottom, we put a meter on the top, and we want to go to centimeters. So we'll put a centimeter on the bottom. And 1 meter is 100 centimeters. Okay, now note that this is meters cubed, right? So this is really a meter times a meter times a meter. So if we do this conversion once, we're only changing one of the meters. And so we have to actually do this multiplication 3 times so that we change all of the meters into centimeters. 1 meter, 100 centimeters. Okay, so now we can make sure our units cancel, right? So we have a kilogram and a kilogram, that goes away. We have 1 meter here, cancels 1 meter there, 1 meter there, 1 meter there, 1 and 1. And so we're left with a gram and then a centimeter times a centimeter times a centimeter, and that is a gram per cubic centimeter. Okay, and then our numbers that we have are 1,400 times 1,000 divided by 100 and 100 and 100. So we could do our factors of, put everything in scientific notation. It would help a little bit right now because that's one of our other topics. So scientific notation, this is 1, 2, 3. So we have 1.4 times 10 to the 3. And then we're also multiplying by 1,000, which is another 10 to the 3. And then on the bottom, each 100 is a 10 to the 6, or 10 to the 2, sorry. So together, 10 to the 2 times 10 to the 2 times 10 to the 2. When we multiply exponents, when we multiply numbers with exponents, we add them. So this ends up being a 10 to the 6 on the bottom. Same thing here, 10 to the 3 times 10 to the 3 is 10 to the 6, and so those actually cancel out. And so our density will simplify just to 1.4, and then we have grams per cubic centimeter. Why didn't you guys tell me I was going off the bottom of the page? Okay, so that's unit conversions. Let's go back to the presentation. Okay, so we just talked about a few prefixes in here in terms of kilo and centi, right? Those are ones that you should know. So these are prefixes that you definitely should commit to memory if you don't know them already. So we have nano, which is 10 to the minus 9, micro, milli, centi, kilo, mega, and giga. Okay, so this is 1 times 10 to the 9, 10 to the 6, minus 6, sorry, 10 to the minus 9, 10 to the minus 6, 10 to the minus 3, and then we go all the way up to a giga, which is 10 to the 9, or a billion. Okay, we just did a quick thing on scientific notation when we did that density conversion. But in general, the rule, right, is that you have one digit, one non-zero digit in front of the decimal, and then you multiply by a power of 10. So in this case, 1500, we look at how many times you have to move the decimal to get in between the 1 and the 5. So 1, 2, 3, 4. So that's 1.5 times 10 to the 4. If we looked at 42.5, I'd have to move my decimal over 1 to get between the 4 and the 2. So 4.25 times 10 to the 1. For small numbers, we got to move it the other way, right? So 1, 2, 3. I have to move the decimal place 3 places to get between the 3 and the 2. So 3.2 times 10 to the minus 3. I'm not sure why we had 1500 twice. Okay, so there's a couple examples to try that we can work through. Let's work through these together. So 125,000 is 1. And then we have 0.00046, we have 12, and we have 2. Okay, so let's go back to our camera. All right, so this one, again, if our decimal starts here, we're going to count how many places we have to move it to get between the 1 and the 2. So that's 1, 2, 3, 4, 5. So that's 1.25 times 10 to the 5. And then this is a small number, we've got to move it to the right. So 1, 2, 3, 4. So we get 4.6 times 10 to the minus 4. And for 12, we'd have to move it 1 place over. So 1.2 times 10 to the 1. And here we don't have to move it at all, right? So it's 2 times 10 to the 0. And just kind of a quick review there in case it's been a while. So 10 to the 0 is 1, right? And 10 to the 1 is 10. And 10 to the 2, right, is 100. Anything to the 0 power is 1. Okay, so on to motion. So we are going to have different ways to represent motion, and the first way that we're going to talk about is a motion map or motion diagram. And you can think about this as like frames of a movie that would be superimposed on top of each other. So instead of seeing where an object was, as the frames are passing you in a movie, you would see them all on top of each other. So our first example is simple: a soccer ball at rest. We wouldn't see it move at all. Then we have this woman running, right? So sort of starting out slow, and then we can see that she's speeding up because the distance, so all of the frames in the movie, right? All of these pictures are going to be taken at equal intervals of time. And we see that she's moving a bigger distance in these same interval of time. So she's speeding up as this goes on. So this is somebody on a skateboard moving at a constant velocity. And we know that because the distance between each picture is the same. Right, so we're not seeing it speed up or slow down, right? So same distance in the same amount of time. And then finally, a picture of a car slowing down, right, or motion map. So it travels this distance, and then less distance, and then even less distance in these equal intervals of time. So it's nice that the examples we just looked at, we actually were drawing out. Well, I didn't draw it out, but they're actually showing the object, the full object, like you would just see in a movie. And after a while, that gets a little cumbersome. So So instead we'll be using something called the point model, and physics, a lot of physics is trying to break down complicated phenomena or problems into simpler models. And so the particle model is one of these models that we'll use, and for describing a lot of our motion. And you can use it when the motion isn't affected by the size or the shape of the object. And that's going to be almost everything that we do until we get to sort of rotational motion, or torque, where we're thinking about really extended objects. Okay, and so what we do basically is represent all of the mass was just concentrated in a single point. And so instead of drawing out a car, if we wanted to show a motion map for a car slowing down, instead of drawing the car at each of these dot positions, right, we could just draw a dot to show where the car would be at each of these intervals of time. So it just makes our, it kind of clarifies the important issues that are still associated with motion. Okay, so before we go now into more detailed description of motion, we need to define some quantities, and in order to understand those quantities, we have to start distinguishing between something called a vector and a scalar. And a vector is a quantity that you need two numbers to specify. It has a magnitude and a direction. So it could be like, if you're driving in your car on the highway going 60 miles an hour and heading north, right, if you're on I-87. So there's the magnitude, which is how fast you're going, 60 miles an hour, and then the direction that you're heading in north. A scalar can be described by just one number, and examples of that would be temperature and mass. Okay, so we can visualize vectors just as arrows pointing in a particular direction, and they have a particular length, right? So the direction is the direction part of a vector, right? And then the length is telling us about the magnitude. So if we want to add vectors graphically, so here's an example of A and B. The way you would do that, right, is first draw out A, then you move B so that when you go from the tip of A, you get to the tail of B. And then the resultant, A plus B, goes from the start of A to the end of B. Right, so that's what we're seeing there. Okay, if we instead wanted to subtract them, so if we want to know what A minus B is, we would start out similarly. We'd just redraw A, and then we'd have to, minus B means it's the same length, it's just going to be 180 degrees, so you're flipping it over. So minus B is the same length as B, but just pointing in the opposite direction. So then we do the same thing, right? So here's the tip of A to the tail of B, and then A minus B would go from the start of A to the end of B, which is what's shown there. Okay, so first main quantity we want to use when we describe motion is the position. So just where is the object? And in order to describe that more quantitatively, we'd have to have some frame of reference. So here, for example, is a car moving, and you can see that there's just a coordinate system here. It's just one-dimensional motion, so we're just talking about its x position. Okay, so that's position, and then displacement is basically the change in position, right? So if we ended up in some final position and we'd subtract what our initial position is, and that's our displacement. It's different from distance, right? So if we see that this car, for example, is going to the right, it stops, right? And then it goes back to the left. So the distance it's traveled is, this distance plus all of this, right? If you were walking that, you would be traveling that whole distance. It's displacement. The displacement doesn't care about actually how far you've traveled in between. All it wants to know is what's the difference between your starting point and your final point, right? Or final minus the initial. That's the displacement. Okay, so velocity is the next important descriptor of motion, and that's talking about how our position is changing as a function of time. So we can just look at a motion map, for example, for an object. Here, that's its location at the first point, and the second point, and the third point. And so you can see that the second and third points are a little further apart than the first and second point. And so the velocity vector, when we can add this to our motion map, which, instead of just having dots, we could have velocity vectors that are going to connect. So like, from 0 to 1, we draw in a velocity vector 1, and then going from the next two dots would be the velocity at point 2. Okay, so here's another example, right, of a hare. So these are going at constant velocity. So this is the rabbit going faster, right, because there's bigger distance between the dots. So all of these velocities would be the same. And then the turtle is shown down the bottom, still going at a constant velocity, but going smaller distance, right, smaller displacement between times. So this is going at a slower speed. Okay, and then we can also do motion maps and show the velocity for things that are not just going in a straight line, but on a curved trajectory, right? So this could be like throwing a ball up, and Jake throws it up, and Jose catches it. So again, you can draw where the object would be at different equal intervals of time, and then again, the velocity vectors would connect those points, right? So they can be at an angle. And just to make the point, it seems kind of weird because you're just drawing like a velocity vector between two positions. But if we look at how we define velocity, it's the change in position over change in time. So really, our average velocity and change of position are proportional to each other, right? It's just this difference of 1 over time that's in there. So, so they're really in the same direction, right, as the change in position. Okay, acceleration. So we can have something moving at a constant velocity, but if its velocity is changing, then we have an acceleration. And acceleration is just defined as a change in velocity over time. And it's going to be in the same direction as our change in velocity. So again, here's sort of the mathematical way we could calculate it. So our average acceleration, we would just along a particular direction, in this case the x direction is our change in velocity in that direction over change in time. And whenever we do changes, we're going to do final minus the initial, right? So it's the final velocity minus the initial velocity divided by time. Okay, so how would we find acceleration from a motion map? So let's just step through the process here. So we're going to start with that first example from the previous page, right, where we have an object that's speeding up a little bit. So because this distance is a little smaller than this distance, so we can add those velocity vectors that we had already had in there that connect the position at different times. And then our velocity or our acceleration is the change in that velocity vector, right? So we have to figure out how much did v2 change compared to v1. So to do that, you can redraw v2, offset from your motion map. And then remember, we're going to subtract our initial velocity. So we have to flip v1 around. So this would be our negative v1. And then our change in velocity is going to be what that difference is, right? So it's going to be from the start of v2 to the end of v1. Okay, and so we see that we get delta v is in the direction that they're moving, right? Which makes sense because this object is speeding up. And so delta v now, remember, is proportional to acceleration. So this is telling us what the acceleration vector is. So to draw the complete motion map, we have, again, our points with the velocity in it. And then at this in-between point, we can now add the acceleration vector that's showing that this object is speeding up in this direction, right? The velocity vector is increasing in that direction. Okay, so it's really this combination of velocity and acceleration together that tells you how the object is moving, right? Because so this is the case we just looked at, where we have an object moving to the right and we have acceleration to the right. And so that means our velocity vector is going to be increasing by this amount at every time interval. So our velocity vector is getting longer and longer, meaning that the object is moving a further distance and speeding up. Okay, so when you have velocity and acceleration in the same direction, the object's speeding up. Okay, if we instead had an object that is moving to the left, right, so it's starting here and moving leftward, but we have an acceleration to the right. So that means that this is our change in the velocity, right? So it means that our velocity vector is getting shorter because we're kind of subtracting a little bit every time. And so that's slowing down. So when velocity and acceleration are in opposite directions, an object will slow down. And then you have a constant velocity, meaning that our motion map would be showing dots at equally spaced intervals. That's only when acceleration is 0. Okay, so let's do an example here of a skier. So this is our problem. We have a skier going along a smooth horizontal surface, and then at a constant speed, and then speeds up going down a hill. And then we want to draw the motion diagram. Okay, so let's go to our camera here. All right, so we have a skier going along a flat surface at a constant speed and then kind of going down a hill. Okay, so we can draw our skier in here. Okay, so let's think about our motion map, right? So constant speed, so let's say this is going to be my first point. That's our skier. I can draw it, to start out with, and then I'm just drawing dots afterwards. So constant speed means that my dots are going to be at equal intervals. Okay, and now as we go down the hill, the skier is going to start speeding up. So meaning that these are going to get further apart. Okay, and then for our complete motion map, right, we want to put our velocity vectors in there. So that will be velocity, connecting our, I didn't do that super great. They're not super consistent, but you get the idea. Okay, and then down here, we're going to see that these object is speeding up. Our velocity vectors are getting bigger. So here, the last thing we need to add, right, is our acceleration. That's 0 here, acceleration. And then in these parts, we have an acceleration that's down the hill, right? And so even if we continued this we go even further. Just so we have another example. And this would be our acceleration vector. Okay? So starting to develop kind of a physical picture of what's happening there. I should draw that a little better, sorry. Okay, back to the slides. All right, so our last topic is just thinking about how we can represent motion more graphically, right? So the motion map is a really visual presentation of what motion looks like, right? Like I said, it's a kind of, like the frames of a movie superimposed on each other. So let's look at this case, right? So we have an object moving. We don't necessarily know, this is actually a student that's walking to school, right? So moving kind of at a constant speed. The student gets to this point and is going a lot slower, right? Because our dots are close together. And then maybe the student realizes that they're late and so it's got to hurry up and finish up the rest of the walk, so going faster there. So remember, all of these dots are at equal intervals of time. So this is saying 1 frame per minute, right? So each dot corresponds to 1 minute of the walk. And so now you can actually plot it. If we have our number line here or our x-axis, you can actually plot where the student is at each of these intervals of time, right? So to start off with, at t equals 0, we're at 0. It's moving up, right, until 3 seconds or 3 minutes, right? Then it kind of starts to go a little bit slower. And then at 6 minutes, it starts to go much faster, right? So the slope of this is getting higher. So flatter kind of starts out with a medium slope. The slope gets flatter when we slow down and then increases even more when the object speeds up. I'm going to skip that. We'll do this Desmos in class. Okay, and we'll finish up with one example here. So the graph below represents the motion of a car traveling along a straight road. Sketch and describe the motion of the car. So I'm just going to sketch the graph on my sheet of paper, and then we can do the rest of the problem. So we have 10 and 20. So we start at, and then we have 20, 40, 60, 80. Okay, so start at 20, or at 10, we move down to 2, minus 20, about 30. Then it flattens out till 40 and goes back up to 0 at 80. And this is again is our time in minutes. Okay, so let's go to Ladybug. So that's my sketch. I just want to minus 10, and this is 10, 20. So this is my x. Uh-oh. Okay, that's my x position in meters, and that's my time in minutes. Okay, so we have to draw a motion map for this, right? What does the motion look like? And then describe the motion. So this is one-dimensional motion, so we can draw our motion map, just along a straight line. So I'm going to draw out my x-axis here, and we'll put our 0 point, and we have 10 and 20, and then we have -10 and -20 and 0. Okay, and then we have we can just mark points here for this time in minutes, right? Or every 10 minutes about where it is. Okay, so we're going to start at, our motion map is going to start with the object at 10, and it's heading back toward the origin, right? So it's kind of moving back to 0, and then back to -10 and -20. And there it stops. Sorry, I should put those all above the same line. Okay, so then we kind of stop there, and now it's going back the other way, going back to 0, but kind of taking a longer time, right? This is like a flatter relationship. So that means that when I go back to 0, so I can kind of draw a big dot there to indicate that it's going to stay there for a while. And when I go back to 0, it's going to take more time. So maybe I can make them like this. Okay, so meaning that we're moving this way initially, right? So the arrows help us figure out the direction of motion, and then comes back to the origin that way. Okay. And then the remainder of the slides we will do in class, lots more practice.